titled Improving Chemistry of Batteries, Improving Vehicle Performance. My name is Johan Blondel. I work at the European Commission in the Clean Planet Directorate that was introduced this morning. And I formed a liaison with the battery partnership, Bat4U, which you probably have heard about. And sorry, now I'm back. And which is going to take over all of the battery research and innovation under Horizon Europe. But here we are still looking at projects that were funded under Horizon 2020 when there was not yet this partnership, so that the activities were a little bit spread. Now, I won't recap all of the points that were mentioned this morning. No, it's lighting, but okay, thank you. So I won't repeat all of the points of this morning about the Green Deal and Fit for 55. I think you know the story by now. Let me just say that it is clear that Europe is going to need a lot of batteries. So depending on the projections, we should see an increase of 15 to almost 20-fold in battery production worldwide. And the ambition of Europe is to become the second player after China as of 2025. And to become largely self-sufficient also in the production of batteries. So you understand that there is a lot of weight, a lot of emphasis on the batteries. And for that reason, this morning we already had a session on the solid-state batteries. And now, this afternoon, we're going to look at some alternative chemistries. I think it is clear for all of us that we are still looking for improved performance and improved safety of the batteries. But the recent developments in the Ukraine have also made it very clear how vulnerable Europe is in terms of dependence on critical raw materials. So some of the projects that we will hear this afternoon are also looking in reducing our dependence on these critical raw materials. So I won't bother you any longer. I know it's just after lunchtime, so the challenge is to keep you awake. Just to give you the outline, so each of the 4 speakers is getting 15 minutes to give a brief overview of their projects. And after that, we will have a Q&A session, which is moderated by Peter Prenninger, who is sitting next to me here. So, without further ado, let me introduce the first speaker. His name is Michele De Gennaro. I hope I pronounced it well. Grazie. He has a background in aeronautics, and I think he is probably the most prolific project coordinator, managing a portfolio of, how many was it, 20 projects? So, yeah. So, Michele, the floor is yours.
Thank you. Thank you, Johan. Can you hear me well? Okay, perfect. Yeah. So, good afternoon, everyone. Good afternoon, ladies and gentlemen. It's my pleasure to be here today and to present TreeBelieve, which is one of the projects that we manage. My name is Michele De Gennaro. I'm from Austrian Institute of Technology. And TreeBelieve stands for delivering the 3B generation of LNMO cells for xEV market of 25 and beyond. TreeBelieve was born out of the LCBAT 5 2019 call, as some other projects that are presented today, and encompass a very large consortium and a very broad spectrum of topics and activities. The consortium is made of 21 partners from 9 member states of the European Union, plus 1 associated country, Norway. And we have, it's a project which is automotive-centered. We do have 2 vehicle OEMs, one for light duty and one for heavy duty. CRF representing light duty vehicles, and Volvo Trucks representing heavy duty vehicles. 5 RTOs, AT, CIC, Fraunhofer, Sealitten, and Enea, one university, RWTH, and 11 additional industrial partners on top of the two OEMs, which are Elkem, Haldor Topsoe, Arkema, Customcell, Insplorion, NXP, Valeo, Manz, Sensichip, ABE, DSM, SNAM. Out of these overall 13 industrial partners, 4 are SME. The project started on the 1st of January 2020, just before the pandemic. We had just one physical meeting, the kickoff, and all the rest remotely. And it's scheduled to end by mid of 2023. So what I'm going to present today are midterm results, interim results, giving some snapshots of what we have done so far. The project has a total funding of a little bit above 10.8 million euro, and it's coordinated by AT. So, 3 beliefs reflect the diversity and the complexity of the LCBAT 2019 call, which was very, very broad. And we see that some of the call under the destination 2 of the cluster 5 steps a little bit back and go narrowing a little bit the topic. Anyway, 3 belief was conceived to be as inclusive as possible for all the topic and all the challenges of the LCBAT 5 call. And it's built around the 3 main activity pillars of activity. The first pillar is a chemistry pillar. We want to deliver a Gen 3B high voltage, cobalt-free LNMO cathode. We want to develop a portfolio of technologies of internal and external sensors, together with a smart BMS and adaptive liquid cooling system for the battery module and pack, with advanced diagnostics and operational function. And we develop in 3 Believe a cradle-to-cradle approach to the battery topic, starting with manufacturing of electrode, cells, module packs, going up to the recycling part, first life, second life, and recycling. And we tackle manufacturability, which is an engineering topic which is very relevant for delivering the Gigafactory volume that we do need in our future in Europe. Finally, the project at the end will deliver 2 battery demonstrators of around 96 cells each, for a total number of cells produced during the project of around 250. So around 200 will end up in the final pack demonstrator, and 50 will be spare for cycling test and recycling test. And each battery pack will have a 12 kilowatt-hour capacity. It will be demonstrated at TRL 6. One battery pack will be fit for 400-volt application, so mainly light duty and small light duty. And another one will be fit for 800-volt application. That's why we want to cover as broad as we can the spectrum of electrified vehicles. So the next slides will be basically some snapshots of the results of the project as they were reported at the midterm. So they are not final, they're not the final results that we will deliver, but give quite a good idea of what we are doing currently. The first slide here, it's about some interim results on the chemistry and the cobalt-free LNO cathode. On the left-hand side of the slide, we see the earliest cycling results on the half-cell cathode. We did develop 3 types of LNO that we have labeled as type 1, type 2, type 3. And what we can see is that we do achieve quite some good cycling results. These results were presented also at the SAE World Congress last year. And we do achieve a capacity between 125 and 135 milliamp per hour gram at half cell level, which is quite close. It's around 80%, 80 to 90% of the theoretical capacity of 147 milliamp per hour gram. That's the maximum that is achievable by the chemistry itself. In the mid part of the slide, you see some results for the half cell type 2 LMO for different types of processing, aqueous processing versus NMP processing. So we were able to develop and deliver such capacity with aqueous processing. And on the right-hand side of the slide, you can see the first results on the full cell. These are not the final cell of 3 Believe. 3 Believe will deliver the final chemistry at the end of April, so approximately 1 month time, but these were some results which are at the moment some months old, where we see that coupling the type 1, in this case LMO, with with an LAP30 electrolyte and the graphite anode, we have a drop in capacities as was expected. And now we are working on inserting silicon in the anode to increase the capacity. We are working on 5%, 10%, and 15% of silicon insertion in the anode. yes, that's the snapshot on chemistry. Moving then to the sensors. A large part of activities of IEEE are about sensors. And when we speak about sensor, we speak about internal sensor and external sensor. For internal sensor, we are developing, together with our partners, a solution for an in-cell nanoplasmonic sensor integration. Basically, it's a fiber optic which is inserted into the cell, and you basically give pulsating lights into this fiber optic, and you study the reflection and reflection of the light within the cell, within the electrode, to get together information about the state of health and state of X in general of the electrode. We were developing the physical integration of this fiber optic. We were developing a board capable of digitalizing the analog signal coming from the fiber optic, and we were working a lot on the packing of the cell itself, avoiding leakage out of the cell itself. Moving then to the external sensor, one of the results that I would like to present today, it's this multi-measurand CMU, where CMU stands for Cell Management Unit. This is one of the most promising results of the project. It's a custom chip which is capable of being attached to the cell and being powered by the cell itself, so it does not need an external power. And it's connected to the electrodes, and it's connected to an external electrode sensor. And it's capable of performing approximately 40 different measurements on live on the cell itself. Some measurements are just thermal measurements, control of the temperature of the electrodes and of the cell itself, internal and external, estimating voltage, current, all the classical parameters, also estimating some gassing, body wetness, and mechanical strain of on the cell itself. So monitoring how the cell develops along its life. And this approach of having a cell-per-cell monitoring at 1 Hertz might be quite interesting for the BMS of the future, collecting data on the first and second life of the cell, as well as collecting collective data for developing smart BMS. Moving then to the third pillar of IEEE, moving to the manufacturing. We have different activities in the manufacturing, one of which is the one that is presented on this slide. In this slide, we are developing and we are testing in our pilot line 880 an artificial intelligence-powered machine to detect defects on the coating. So on the left part of the slide here, you see a very simple schematic of our coating machine. After the drying of the electrode, we have a camera, and the camera observes basically the coating, basically flashing different types of light and igniting some different optical phenomena in a way that we can detect imperfection on the coating itself. And we are using a machine learning algorithm, so the camera and the algorithm behind should learn how to detect these defects and inform the pilot line automatically. And at the moment, we are training the algorithm to detect defects, placing manually some defects on the coating itself. And last but not least, among the results that I want to present today, it's about the Gigafactory process modeling. This is a less scientific, a little bit more engineering part of the project. Here we have modeled, together with our partners, the overall processes that a Gigafactory should implement. So basically, we went through all the steps for delivering a Gigafactory capable of 10 gigawatt-hour per year of production. And we have modeled all the single steps one by one, and we are now putting together this to get an overall factory model. We have some of these steps are reported here. We have the electrode production, the cell assembly, made of notching, electrode cutting, lamination and stacking, taping, tap trimming and welding, deep drawing and packaging, and electrolyte filling, and finally cell finishing. And the animation that you see on the screen basically concern the tab trimming and welding, just as an example. And beyond the animation itself, what we can get out of this modeling is a model of a Gigafactory, how we have to build a Gigafactory. This is a recipe that we are searching for. And what is the throughput of this Gigafactory, and what is the energy intensity that we need to invest in the Gigafactory to deliver cell. These are very important aspects that we do need for delivering the European battery manufacturing industry. moving ahead, I'm coming to the conclusion of my presentation. Believe also collaborates with, of course, other projects which have been funded under the same call, the LCBAT 5. We have formed, together with other projects, an LCBAT 5 cluster, which is made of Cobra, which we'll present just after this presentation, Hydra, and Sense. And we have had so far 2 events, one in November 2020, the Battery of the Future webinar, and one in June 2021, the U Green Week. And we're planning another one for May, as well as we issue a joint newsletter. We are looking for cooperating also with other projects. As we know, the Commission recently concluded the Destination 5, the Cluster 5 Destination 201 or 2 call, which is again on the Gen 3B. So we are looking forward the winners of that one for cooperating together. And in terms of impact of the project, Believe aims at building capacity for the European battery manufacturing industry along the full value chain, trying to touch all the process from the raw materials up to the recycling and having a circular approach. As I said before, we do develop cell chemistry, sensors, and manufacturing, and we have a very strong environmental focus, which is beyond the topic itself. It's also about recyclability. We have also recyclability activities within the project, and at least at lab level, we're going to dismantling the cell at the end of the project and see how much we can reuse of the raw materials. This is my last slide. I invite you to visit www.3believe.eu and to visit our Twitter account and LinkedIn account. We keep this always up to date. For any further question, you can either contact me, michele.degenaro@at.sc.it, or my colleague Boshida, which is the coordinator of the project. Thank you for your attention.
Thank you very much, Michele, for this very smooth and interesting introduction of 3Believe. Let us now pass to the next speaker. It's Dr. Jordi Jacas. He is a leading researcher for the battery section at the Catalonia Institute for Energy Research, and he works on next-generation batteries, including lithium, sulfur, and generation 3B. So, the floor is yours.
Thank you very much. I confused that.
On the name of... Oh, okay.
It is not.
You go to... No? Sorry.
I give you 2 minutes.
It's cool.
Yeah. Great.
Okay, I clicked
Thank you very much. Well, thank you very much. Indeed, it's a pleasure to be here with all of you. Thank you for the invitation. COBRA stands for Cobalt-Free Batteries for Future Automotive Applications. And COBRA is a research and innovation project, obviously, and started in January 2020, and the expected end of the project is December 2023. The COBRA project was granted with a total of 11.8 million euros, and the consortium includes 19 partners. 3 of them are universities, 7 RTOs, 4 SMEs, and 5 enterprises. So the aim of the COBRA project is to develop a novel cobalt-free lithium-ion battery technology, and we expect to demonstrate this technology at the TRL level 6, which means the battery pack level. Regarding the objective, we have very specific objectives, which are also very challenging. Regarding the cathode, we are working with a new and more exotic compositions, which are called lithium-rich oxides, which are composite oxides of rhombohedral and monoclinic phases. And we are expecting to reach discharge capacities beyond 250 milliampere hour per gram at low C rates, together with a long cycling of 2,000 cycles. And obviously, we are looking for fast charging up to 3C, delivering between 100 and 150 milliampere hour per gram. We have similar objectives for the anode, which is a silicon graphite composite. So we are looking at high capacity, high cycle life of 2,000 cycles, and also to be able to release capacity up to 3C. This is obviously complemented with electrolyte to ensure SEI and cathode electrolyte interface formation at both electrodes and to perform stably beyond 4.5 volts. At cell level, energy density is one of the main targets, which is 750 watts-hour per liter, together with fast charging. This is going to be complemented with advanced BMS to ensure and improve the performance of the cells and the batteries, together with weight reduction of the final battery pack down to at least 50% of this weight, battery pack weight. Regarding the safety, environmental, and financial, we also have very optimistic and specific objectives, which are increase the safety using extra additives to reduce the flammability of the cell, improve the safety of the battery housing, able to contain the fire for at least 30 minutes, increase the housing tensile strength and the impact resistance of the battery pack. And all of this is going to be complemented, which is the main point of the project, of getting rid of cobalt completely from the battery itself, using a life cycle assessment right from the beginning, from the materials and the components, attain 95% recyclability of the metals, fabrication of green and recycled battery housing, together with the silicon materials that we are using for the anodes are recycled silicon materials from waste stream. Finally, the financial aspect or objective, which is shared with all the LC BAT5 cluster, is to reach 90 euros per kilowatt hour for the battery pack. When it comes to results from these very ambitious objectives, we can start with a cobalt-free cathode. As I was mentioned, this is a lithium-rich oxide, and currently we are looking at Li 1.2 rich compositions, and we are able to attain nearly 200 milliampere hour per gram with capacity retention of around 95% after 150 cycles. The materials are able to supply capacity 100 milliampere hour per gram at 3C, and we are very interested in looking and understanding these materials from the microstructural point of view. So we are realizing that depending on the dopings that we are using, we are changing from a segregation of the different phases, the rhombohedral and the monoclinic, to a more the formation of nanodomains within the particles, that is affecting a lot the performance of the electron materials. Regarding silicon, we are currently using 10% weight of silicon, combined with graphite. We have good cyclability for the silicon, the recycled silicon, as I mentioned. This is recycled silicon that is coming from different weight sources, so we are using the recycling of the photovoltaic panels, for instance, so we are using a lot of treatments for making this silicon active and to perform it as the way you can see it here, so delivering capacity of around 700 on the initial cycles and then down to 400 milliampere hour per gram. And this silicon is also able to deliver capacity up to 3C, which is 475 milliampere hour per gram. Following up with the electrolyte, obviously, as we are having two materials that need to be formed in a very stable way and operating at high voltage, we have a lot of research on the electrolytes, looking at ionic liquids and new formulation and new additives. So these are representative figures of the profile of the cell. This is full cell results, the one that you can see on the left-hand side, on the top side. So the characteristic plateau of 4.5 volts, which is characteristic of these lithium-rich oxides. Also, we are looking at these additives to increase the stability, as I mentioned also, as a function of the flash point and a function of the conductivity for these electrolytes in order to get good performance at high C rates. And also, good results we are obtaining with ionic liquids, so we are managing to push the capacity of the cells up to 210 milliampere hour per gram at C/3 using ionic liquids. Regarding cell level, we are very active also on this topic, so we are trying to upscale our green processing for the cathodes, for like the assembly of the cells, and achieving capacities beyond 200 versus graphite. And also we are assembling many cells using LTO as a reference and counter electrode in order to monitor the impedance and improve the stability of the cell. Following up with our cells, obviously we're going to be assembling these cells in modules. We got these modules and we are going to include obviously many sensors in that modules, and we're going to have wireless communication between these sensors. These sensors mainly are going to be impedance, temperature, pressure, and strain, together with gas sensor as well into the battery pack. And that is going to be assembled as in a form of a battery pack, which is going to be green and recycled using wood and aluminum. Obviously, for the validation of the battery pack, we are using real driving conditions. The aim is to use this battery pack in a urban electrical vehicle. So we are looking at 30 kilowatts hour battery packs for power up these light vehicles. And obviously, I was mentioning right at the beginning, we are doing following up the environmental impact of our technology right from the beginning, using life cycle assessment, cradle to gate in the project. Just following up with my colleague, Michelle was mentioning, so we have been very interacting with the cluster LC-BAT5, so we have been doing sharing newsletter, we have been actually sharing also different meetings. Michelle has already mentioned them, so it's not really important for me to go again through them. And regarding the impact, in the frame of the project, we are expecting to have generation X pound cells, which is going to be like capacity of between 30 and 40 ampere hours. These are going to be large cells for the project, which is challenging to be released now, soon. So we are expecting that's, sorry, this is going to be August 2022, sorry. We are expecting generation 2 is going to happen now, but the final cells are going to be in August 2022. Obviously, this is going to be complemented with our advanced BMS system, which is going to be the beginning of 2023. And then in the middle of 2023, we're going to have the assembly of the final battery packs, which then are going to be tested in the test bed. And finally, just to complement this impact in the frame of what the Cobra project is going to add value into the society. From the technical point of view, we're going to aim to demonstrate the technology, this lithium-rich technology, challenging, but we expect to be there. Obviously, to keep working on the silicon anode, so we hope to complement the effort that many people is doing on the silicon anodes, improve the cell chemistry, and obviously to reach the ambitious targets of energy density of 700, 500 watts hour per liter, and obviously introduce new smart sensor and advanced battery management system. And to finish up, regarding environmental and cost, so far I know Cobra is going to be, well, together with my colleagues, cobalt-free technology, which is challenging, especially either in terms of capacity or in terms of voltage. So we are working towards that direction. And the ultimate goal is to accelerate the implementation of Generation 3B lithium-ion batteries. Thank you very much for your time.
Thank you very much. That was a very quick introduction. We're well ahead of time. So then we will move to our next speaker, Dr. Michela Ottaviani. She works at the University of Limerick in Ireland, and she is an expert on silicon-based anodes for advanced lithium-ion batteries. Yeah. So the floor is yours. Thank you very much.
Sorry, just for trying. Yeah, my name is Michela Ottaviani. In this moment, my name is Michela Ottaviani. In this moment, I am glad to represent my group in the University of Limerick that is leading the SiDrive Project. SiDrive Project is an ambitious project where we are basically define a new chemistry for the lithium-ion battery cell. I will describe more in detail later. It's a project that is having a funding of about 8 million euro, and is involving 16 academic and industrial partners that are all spread along Europe and specifically along 7 different countries in Europe. And the project coordinator is Professor Kevin Ryan from the University of Limerick. So, as I was telling before, our ambitious project is to create, develop and demonstrate an innovative cell chemistry that is based on high voltage lithium-rich cathode and a polymeric-based electrolyte and a silicon-coated 3D nanowires anode. Which is the vision of the SiDrive project. We are thinking that our main object will be to demonstrate at the end of this 4th year that is started just in this February 2021, because the project will proceed until February 2022. So we are a little forward the midterm. And we will be able to demonstrate a TRL5 for a prototype with high energy density, long cycle life, fast charging, and of course we have to consider also the safety aspect and recyclability. Which will be the impact of this project is to increase the European batteries competitiveness, increasing the electric vehicle uptake and reducing the consumer cost and the greenhouse gas. For the anode development within the work package 1, the University of Limerick is leading this work package. And basically what we are doing, we are developing a nanostructured current collector that is a copper silicide core that is surrounded by a high loading amorphous silicon coating. At the moment we are at the stage of 1 mg per centimeter square of amorphous silicon that we are able to deposit. And as we all know that silicon is having the drawback of a very high losing of the initial capacity, so we are working in collaboration with the KIT on using the extra capacity that is coming from the lithium-rich cathode for compensating this capacity loss. Unfortunately, I don't have the graph of the very last result, but at the moment we achieve about 350 cycles with the capacity retention above the 90% with these strategies. As the main aspect of our project is to go from a lab scale to an industrial scale, we are in all the work package paying a particular attention on what is the upscaling. At the moment, from the work package 1, we are able to provide to our project partner a prototype of anode that are having an aerial surface of about 30 centimeters square, because our partner of the work package 4 at the moment are working on small prototypes of pouch cell. Which is the target for the anode site. Our target is 100 cycle in a full cell configuration with 80% of the capacity retention at 6C. Here I'm showing just the preliminary results that were fundamental for us for identifying the best composition of the ionic liquid electrolyte that demonstrated to be the most promising one regarding the anode side. For the work package 2, the leader of the work package is the ENIA Research Center, and we are developing ionic liquid-based electrolytes, and we embedded this kind of electrolyte in a polymer matrix thanks to the collaboration with the Politecnico di Torino. And what is crucial in this particular aspect of the electrolyte, we are always monitoring what is happening at the interface between the electrolyte and the anode. So we are monitoring the SCI composition for understanding and for having feedbacks from this kind of analysis for understanding the properties of all the materials involved in the project. At the moment, with this kind of electrolytes formulation, we are having high capacities with also for the high current above 2C, and this is really promising results. As I was underlining from the anode side, our main target is to upscaling every specific part of our cells. So also in this case, in collaboration with the Solvoionic, we observe that we achieve an increase in the volume and in the yield of the electrolyte that can be promising for an upscaling production at the industrial scale. Regarding the cathode development within the work package 3, this part is led by the KIT. At the moment, we achieved the 80% of the capacity retention after 500 cycles with the most promising formulation of the ionic liquid. Because of the nickel content of the cathode, we are also working on the artificial CEI for trying to have a better control on the cathode side. This kind of ionic liquid electrolyte, as is showing the graph in the center, is showing an outstanding performances as compared to the standard electrolyte that is the carbonate-based one in red. And the most important aspect for us on using this ionic liquid electrolyte is to avoid any kind of flammability of the cell, and we demonstrated that this is possible. Again, by having a view always focus on which is the upscalability of our material. At the moment, we are able to provide to the partners a cathode up to 5 kilograms for having a larger scale production. Regarding the work package 4, that is the full cell testing, we are having the leadership of the SiDrive that is working on the full cell harmonization with the anode and the cathode and the electrolyte that we are providing them. They are, at the moment, at this stage, they are comparing the performances of the silicon nanowires based electrolyte with a more standard silicon graphite based anode for understanding for the different current which are the performances of our anode. And again, the most promising formulation of the ionic liquid electrolyte is the same that we observe within the other work packages. Regarding the work package 5, we are having very important feedbacks from our partner DLR, because they are working on the modeling of our material, and this is another important aspect that is giving to the material people very important feedback, especially regarding the interface between the electrolyte, the anode, and the electrolyte of the cathode, because we all know how it's crucial to having a good SCA and CEA formation. And through the simulation model, we are having feedbacks regarding our materials. By going on to the work package 6 that is leaded from FAM, we are going from the lab scale to a more industrial scale, and they are analyzing small prototypes, and they are also evaluating industrial protocols for the cell testing and the aging. Here the main aim is to achieve the fast charging for our cell that is at 6C, that is corresponding to 10 minutes of charge. And at the moment, this is the very initial results that we are having with a silicon graphite blend. But in these months, we are working on testing the silicon anode-based material. Regarding the last work package, that is the work package 7, we are having a lot of attention. We are paying attention on which can be the real feasibilities of these prototypes that we are developing, and again, by having a view focus on which can be the perspective at industrial scale, we are working on the design of the demanufacturing and remanufacturing process with an automatic process, but we are also paying attention on which is the recycling of all the materials that we are using for our cell. So at the moment, we are between the TRL4 and we are moving to the TRL5, but the project, of course, the ambition of the project is to go beyond the project that they will finish in February 2023. And our aim is to develop batteries that can be used in a real electric vehicle, and with a target of achieving above 450 watt-hours per kilogram by 2030. By going a little bit more in detail, after the demonstration of the TRL5 by the end of the project, with an energy density between 350 and 400 watt-hours per kilograms, what could be refined by the 2030 is a phase one, when we can refine the cell chemistry for demonstrating the progress from the TRL5 to the TRL7. And then we can go through a phase two, when we can really work on the production upscaling, and by demonstrating the progression between TRL7 to TRL9, and demonstrate the performance of an electric vehicle. And then the final target by 2030 will be the application in a real electric vehicle, and this can be a very strong improvement regarding especially the environment impact, because we are all hoping that we can have more electric vehicles by the date of 2030. Thanks a lot for your attention. That's all from my side. And if you need more information, you can contact me or the project coordinator, or can have a look at our social media and website. Thanks a lot.
Thank you very much, Michela, for another very interesting presentation. I would like to remind you all that we have time for questions after the last presentation that is coming now. So please write down or memorize your questions and responses for then. So now the final presentation in this session is given by Christophe Aucher, and he is working at Leitat in Barcelona, where he works on the energy storage team. So Christophe, the floor is yours.
Thank you for your invitation. And it's really great to see all of this face. This is a long time ago. So firstly, in this first slide, a snapshot about lithium sulfur activity worldwide. Lithium sulfur existing since 15 years ago, but really at a company level, I believe just before year 2000, it was some company working there, maybe firstly Lithium Power, and after Oxys that has been starting in 2004 and finishing in 2020. Obviously the champion is LGChem, but you can see that since the last 8 years you have several spin-offs that has been developing prototype and pilot manufacturing around this technology. So it is definitively TRL57 for this technology. And regarding the performance, you have kind of threshold between energy and cyclability. So high energy density, low number of cycle, and lower energy density, you can reach something that it is comparable to lithium ion, for example. What it is important to take in consideration, recently in Nature, at the beginning of the year, I see at least 2 publications claiming plenty of cycle for lithium sulfur. But what you have to take in consideration, it is what you have in this on the right, is the format of the component that you will put in the cell. Is meaning that if you want to reach something above 400 whatever per kilo, you have to respect this KPI. And in none of these articles are respecting it. So it is why you have always something different from what you see from the literature on what it is really possible to be done at industrial relevant level. So LISA is a 14 partner project, 8 million euro, 100% funding by the European Commission. We lose Oxys on May last year. Oxys was a company that was dedicated to the lithium sulfur manufacturing in England. And we replace them by Nextech, that they are based now in Italy. Originally they come from California. The CTO is the ex-CTO of SATKI, for people that know about solid state. So they joined the consortium since November to take the lead on the task done by Oxys. Many of them, I believe, the 5 first partner, so it's coordinated by LETAT. The 5 first partner basically is coming from the previous SiDrive project. So the KPI are like everybody, to make a safer and more performant technology than what it is available. First SiDrive project was based on a plug hybrid vehicle, so much more to make it working on power. Is big limitation for lithium sulfur to work on power. On also volume is another limitation. So we really target bigger battery pack on the full electrical vehicle, like bus, a bit the same tendencies that we can see for hydrogen, for example. This is overall result up to now. So the project will finish at the end of this year. So our baseline is coming from SiDrive project. So here you have the link to see more on that. Basically, we stop at 310 watt per kilo at more than 10 ampere hour push level, which is relevant. On November 2020, we achieve 400 watt hour per kilo, 450 watt hour per liter at 18 ampere hour at cell level. Lisa was really focused on manufacturing because this is something that we saw from the first project, that if you want to make plenty of push cell, more than 10 ampere hour, you need to have component at this level. So we develop hybrid solid electrolyte by coma bar process on the different strategy for cathode. At least we have 3 different manufacturing for cathode that are providing this 400 watt hour per kilo at cell level. On different strategy also for coating with inorganic solid state electrolyte on membrane and on lithium to make our own lithium also, as we saw sometime this day. And we develop both model in terms of push cell and cylindrical cell on all what it is state of health estimator and state of charge estimator that I will show you several. This is what we get regarding pulse laser deposition process. So you can do it. We can do it by roll to roll. Basically, to make on our lithium, here you have in comparison to bare lithium. So you see that with a limited thickness of lithium, you reach a similar result that using bare lithium. And the idea was to make a succession of layers on the top of it. So lithium, lipon, sulfide with the same process. Here you have LGPS on the top of a specific separator that we developed by electrospinning. Why we use nanocellulose in this case is because you have an unseed thermal property respect polyethylene, that it is baseline for separator for lithium-ion battery, polyethylene, polypropylene. Nanocellulose give you much more temperature for the processing, so this is also important parameter when you want to make physical deposition or this kind of things. The conductivity is not excellent. We get a lot of issue with this material. It is sensitive to everything, to humidity, the manufacturing, and once the cell is reacting with the electrolyte, it's really, really tricky to work with sulfide. This is a generation that we did in November 2020. So this is almost 20 ampere hour cell level. That is giving more than 400 watt hour per kilo and approx 450 watt hour per liter. So yeah, pretty online with what you can find in the state of the art. This is another process for making cathode manufacturing. So here we do Arkema do a material by co-extrusion together carbon nanotube and sulfur. And after you have the process from Fraunhofer that it is dry processing, is meaning without solvent. So you have this 3-roll mixer now, and basically you can lift up the cathode from your current collector. So dry manufacturing. This is solid state battery, maybe one of the first for lithium sulfur at least. So here we can see that we reach almost the theoretical capacity of the sulfur, but It could be that the solid-state electrolyte is participating also to the reaction, but at least this is a kind of first proof of concept without using electrolyte. Here the cell is a push cell of 6 ampere hour, and it is a solid sheet of each component, no? Lithium, solid-state electrolyte, and the mix of cathode and solid-state electrolyte. So really without electrolyte. This is the first result from Nextech now in the consortium. So here you have more than 1,000 cycles, 82% of the retention of the initial capacity for lithium sulfur. So here it is limited. This is not 80% of the dip of discharge. This is 50% of the dip of discharge. So it's meaning that you do not have any more this 400 watt-hour per kilo, but you have to divide more or less by 2. But it's to illustrate what I was showing before. Here you have 2 configurations, one at more than 400 watt-hour per kilo, the other at 370 watt-hour per kilo. So what you can get in terms of cycle, depending how you make working your cell, no? Basically, I did not enter in detail, but from Nextech they have a different strategy that ever what we have been done here regarding the solubility of polysulfide. So I will not enter in detail, but if you have different density of cathode, you have to adapt your electrolyte too, and so you can promote high solubility of the polysulfide or clustering of the polysulfide, no? And if you go for one direction or another, you have one result or another. This is a result on the hybrid solid electrolyte coating by Comabar on polyethylene separator. So this is ceramic lithium conductive material that it is embedded in polymeric matrix. Here we reach 7 micra of thickness on the top of the separator. So you have we have been working a lot. We meet a lot of issues to make stable the composite because the ceramic surface is reacting with the polymer and with the humidity, no? So it was not easy to make it stable. And also it's not easy to make it at 7 micra because the particles in general are bigger, 20 micra or superior. So you have to pre-treat and to post-treat your material to reach this result. Here what we get, so this is coin cell. All the other was push, this is coin cell. We have been sent the material to Fraunhofer on Nextech this month to Nextech. For evaluating at larger scale. But basically what we see, if I can, yeah. So here you have the bare material, no, as received material, the black one. So you can see the decay that you have now without coating. And what we see seems to be that when it is coating, you add some resistance in the cell and you maintain longer the capacity, no? So we are in the way to test it today in push cell. This is the estimator. So for people that know, lithium sulfur is not working as lithium ion. This is not the same voltage. This is not the same behavior with the temperature, the seal rate, etc. So you have to build other algorithm to control the state of charge on, in this case, state of health also. Here, following 3 different methods. So all of this, it is published. This is aim also to know how much you get from the first life to be able to use it after, no? So this is available. We have been working on the recycling. So here this is a water-based recycling. So we can see that depending the parameter that we apply, we can reach more than 80% of lithium recovery. Basically in the cell you have carbon, sulfur, aluminium, copper, lithium. So the metal of interest is lithium. So this is done also. Regarding the impact, so as you know, no, this slide has been done before the conflict with Russia. You know that today nickel is about more than 100,000 euro per ton. Basically, sulfur is more expensive to transport sulfur than to buy sulfur. we know that from the 90s, always we have been have some issue regarding the supply chain. In the past was cobalt with different with unstable region, no, and today is nickel. Since the 19, always we have been depending from someone on somewhere. Sulfur is coming from Europe, is a waste from the oil industry, on the chemical industry, so we have plenty of sulfur. On the cathode is only sulfur and carbon. So the safety regarding the internal core circuit, it is safer than lithium ion, and it is adapted to the current manufacturing. This is in corn coating. I show you other process like the dry processing, but the cell that was done by Oxys, for example, was following this. I guess this is picture from Oxys. This. Regarding the application, so we believe that today it is okay for all what it is drawn, so all what it is low level of cycling, no, on required to be light also. So we believe that it is ready today. It is integrated already in some of this application. After, basically, more cycle we will get and more application we will get, no? Together with the issue that we have regarding the power, to give you an idea, all the curve that you see are cycled C/5 or C/10 for the solid state, for example. And when you reach 2C, you are more or less at 70% of the C/5 beginning of load, no? So cyclability and power are really two drawbacks that are not solved today. But more you will increase this parameter, more you will get application. It will be very tricky to address it to a passenger car for power, etc., and volume. But we think that for this application, this is something completely possible. Some link regarding the different projects that some partner of LISA are working with. So none of them inside BEPA or Battery Europe or LCBAT and so on, but from UK and from Germany, there is some programs that are promoting lithium sulfur. And that's all. Many thanks.
Thank you very much, Christophe. I would like to thank and congratulate the four speakers for doing a brilliant job. First of all, I've seen that the whole audience has stayed very attentive, which is a challenge after lunchtime. Secondly, you have managed to stay well ahead of time, so that leaves us more time then for the question and answer session, which will be moderated by Peter. So we will have, well, almost 40 minutes for Q&A now.
Thank you and good afternoon, ladies and gentlemen. Yeah, basically to open now the Q&A session, I would have a lot of questions, but it's, of course, I'm looking in the audience if they're popping up first questions. Yeah, please.
This is Pietro Perlo. I have several questions, but let me start with our friends there on the silicon layer. For a battery manufacturer, it is very important to understand what it is the electrothermal deformation of a cell. Now, many recalls that we have seen in the years were because the people that were designing the battery pack didn't think at all that a cell is a living creature which gets old. Okay, so if you have an NMC cell, when it is new, typically it deforms from 1%. Getting old, 8 years, it may the electrothermal deformation is 8% or so. This now is also reported in some data sheets of the largest manufacturer. Now, when you go to high content on silicon, you have 8% when the cell is new. So the question for you is, do you already have any data on the electrothermal deformation over the years? Because you start from 8%. And if you don't want a fisarmonica, we say in Italian, in English, accordion, you need to know where you are going over the years, okay? I don't know what happens for the sulfur, but for sure I know what the importance of this is for battery manufacturers. Do you have any data, or are you going to plan any test over the years in this?
Thank you very much. That's on deformation. Hopefully your mic is working. If you check.
Like that? You want to answer first? Okay, so I will go for lithium sulfur. In the third project, Alizé project, I believe you have the link in my presentation. We did module on pack. So for lithium ion, better you have the pressure and better it is, no? For lithium sulfur, it is breathing. So you have to, for the strategy that we use for the module manufacturing, was to give space between the cell and to let them breathing, no? Is a bit difficult because of the lithium stripping plating, the lithium metal, you have to apply pressure is better, but for the sulfur, you have to no apply pressure, no? So this is something that I did not show, but with different electrolyte, different type of cathode, you have to apply, or some of case, you do not have to apply pressure. So we are aware about the volume expansion for lithium sulfur.
Do you have any data, plus or less a percentage?
I can, me myself, no, but I can know the whom can have this data.
Okay, thank you. Maybe Michaela.
Yeah, sorry. Can you hear me? Yeah. Yeah, it's a very good question because it's a very tricky part of the work. We still don't have data, but we are planning to go for this kind of test because it's really crucial test. Yeah.
Okay, thank you. You want to add?
I don't want to add much. In Cobra, we are in the same situation, so we don't have any yet, the final demonstrator yet in terms of cells. So we expect to do such experiments and such testings, once we have the cells. So that would be.
Okay, thank you. Further, there's another immediate question. Please state your name and affiliation maybe before you start.
My name is Dieter Seppai. I'm from Botswana. One question which is maybe as well linked to the breathing behavior. It's so far as well in the morning session, we have heard always on pouch cells. Do you think as well on different styles like cylindrical cells? And is as well linked to this topic is if you have a sensor, can you imagine that you can integrate it as well in a cylindrical cell?
Maybe I can start. From the TRIBELIEF perspective, pouch cell are the one that we are going for. So we don't envisage other formats other than pouch. This is a given specs from the automotive industry for maximizing energy density while minimizing cost, which is one of the overall and overarching target of the project. So I cannot basically say more about cylindrical cell. We don't have direct experience with that. We go for pouch. Concerning the sensor part, the sensor that we are developing in TRIBELIEF are designed to be integrated in a pouch. For the in-cell sensor, I don't see this as a possibility for other formats like the cylindrical. For the CMU, for the external sensor, of course it is. Might be that we don't need all the measurements of the multi-measurement CMU, especially those which regard the mechanical properties, which are tailored to be pouch. But for the other, yes, it's a possibility.
Anyone wants to add something?
For lithium sulfur, we are trying both cylindrical and push. Seems to be that cylindrical is not good option for lithium sulfur. To give you an idea, for lithium ion in 18660 format, you reach 3 ampere hour on nominal capacity. On lithium sulfur, you will be half of it. But we have the feeling that maybe if we switch to solid state, maybe it makes sense to have something that is minimizing the space that you have for the electrolyte. And regarding the cost, evidently is much more cheaper to make cylindrical than push. So some of the partner of the consortium already detect a non-automotive market that could be interesting for sulfur, because at the end, regarding the material that you are using, if you sum ship manufacturing also, you have another type of market for this chemistry, whereas the performance are lower. So today I would say push for lithium sulfur, but I do not discard that that cylindric could be an option in the future.
Maybe before handing over to the audience again, may I add a question? Certainly interesting having sensors well integrated, well embedded. Maybe you could all try to comment getting rid of real sensors and integrating virtual sensors instead of. How do you see that for your technologies?
We did it in Alizé. I believe it is reported. So it was deformation sensing. If you are looking on the discharge curve of lithium sulfur, it passes at least 3 times by the same voltage, no? So it's super difficult to make Coulomb counting, no? Or to check it by impedance. Yeah, you have a peak of resistance when you are the first peak of discharge, no? But basically, what we did in Alizé is to monitor with the deformation. On the deformation, follow pretty well the state of charge and discharge, no? So deformation sensor for lithium sulfur.
Anyone else wants to comment on virtual sensors? No. Okay. Yes, Pedro, further question?
Yes, another question, but very much related. Oh, please, excuse me. Very much related to yours, Peter. But this is for Michele. So let me start with a very provocative example. If you don't measure the temperature, or if you measure the temperature of your body with a very light sensor, you sometimes you don't understand you have fever. But if you put a sensor which weighs some 100 kilograms in your head, even if you don't have fever, after 1 hour you measure fever. So the question for Michele is this. You are designing a 48 watt-hour cell, because you say you have 250 cell in 12 kilowatt hours. So just making a simple, you are saying that you are putting a sensor per how many layers in every cell? Do you have 8, 10? How many?
No, it's larger. The cell is larger. 250 cell is the full amount that the project will deliver. For each pack of 12 kilowatt hours, we are embedding 88 cells or 96, depends on how many models we put inside. So the cell is larger. The cell is 135 amp per hour.
But how many sensors do you have per cell?
We have, for the external one, we are planning to have one demonstrator with 1 cell per sensors. For the internal one, we are keeping this at the lab level.
So if you have 8 layers, you have 8 sensors, which is indeed the case of the 100 kilogram temperature, because the sensor is very invasive, and coming to what Peter was saying, it's very invasive in the electrode. It is not just something there looking at.
It's not that invasive. We want to try in Tribelieve and in this research project also a cell per cell monitoring to see how far we can go, and then tailor the design of the sensor for the type of application. There are, just diverging a little bit, we are thinking cell for different kind of application. Tribelieve is an automotive one, so most likely will not need a cell per cell sensor, but might be a test bed to also explore other approaches which might be used in some other application. If I think about an aeronautic application where safety has a different meaning, there we might have a cell per cell sensor. So we are trying to use the technology to try different approaches and to see where the industry is pushing or pulling forward for different application. But at the research level, on one module, we are going to try a cell per cell sensor approach.
Thank you. Maybe before handing back to the audience, a question for Jordi. In your application, you have stated an increase of the housing strength, the tensile strength and impact resistance, and you're mentioning you're aiming at a 4-time increase, stronger than steel. Could you report on progress towards these targets?
Thank you. Well, frankly speaking, I don't have the numbers right now, so that was one of the specific objectives of the project, and that was put on the frame of the green and recycling new battery packs. Also in the frame of like improving the fire resistance of these battery packs, and in line with this improvement of the resistance of these battery packs. So I'm sure these tests have not been conducted yet. The battery pack has been designed and has been manufactured, and that is next on the ladder to be conducted.
So you can't report anything about the ideas, what materials or what, because I mean
Yes,
that's something a little bit in contradiction to recycling.
No, it's going to be wood. Wood, if we're going to be using, are we using wood? That is what I mentioned during the presentation. Wood is going to be the main component, and together with recycled aluminium. Okay. So that is going to be the 2 main components of the battery pack.
Okay, thank you. Thank you. Yeah, maybe in the meantime, someone has got. Yeah, there's obviously a question in the back.
Very briefly, thank you very much. Lithium sulfur looks to be a very promising cell. It's the energy density is huge compared to the other one. What do you think is missing? Do we need to know, for example, to better understand the mechanism of the sulfur cathode to get a better interface metallic lithium electrolyte for the solid one, or even the same question on the anode side is for the other project? Thank you very much.
Yeah, I believe there is a lot of similitude between the ongoing project. At least for lithium sulfur, I believe we can share work between the work that is been done regarding the lithium. And for the lithium sulfur in particular, we have to understand better how is working the ion transport mechanisms, in terms of bulk interface on interface. As I've been shown today, we have some example of solid state battery that are working, so we have to understand how it is working.
Okay, thank you. Maybe I have a question for Michela. You have in your presentation, you have talked about nanostructured current collectors. So nanostructuring is fine and usually certainly improves performance in different aspects, but sometimes it's a little bit an issue regarding long-term or cycling stability. Do you have any results, any ideas about the long-term stability of those nanostructures?
Well, thanks for the question. The good challenge for us was the stability of the anode, because we all know that silicon has many issues. The most important is related to the volume expansion. But the innovation we brought with this kind of project is that our core, that is the copper silicide nanowires, are coming directly from the substrate. So it's a very stable structure on when we are depositing the amorphous silicon. And regarding the advantage of having the nanostructure is not only that we are having the active material that is perfectly anchored to the substrate, but by having this porous structure, this core, also when we are depositing 1 mg, unfortunately I didn't show the image, but the interesting aspect is that we are still having enough space between the different nanowires, even after 1 mg per centimeter square deposition. So we are enable the breadth of the silicon, and we are having a very stable performances, especially after the pre-lithiation, because as I was telling before, we are having a very stable cell after 350 cycles with a 90% of capacity retention. That is really impressive for us, because we all know that the main challenge for the anode was the stability along a very big number of cycles. I don't know if I answered to your question.
Interesting, yeah. Yeah, a question to the audience, maybe someone. Yeah, you've got a question in the middle of the audience.
Thank you. Yeah. Brian Robinson from Zemo Partnership in the UK. I'm not a technical battery expert at all, and you'll probably understand that when you hear my stupid question. But it's more sort of the fundamental nature of the research, and it's a question for all the panelists really. It seems to me, as a non-expert, that battery technology is moving on at an enormous pace. Pretty much every week I hear of a new breakthrough. And it may be in Europe, it may be in the States, it may be in Korea, it may be in China. Everywhere is working in this field and making rapid progress. So to what extent do your projects, many of which were, I guess, proposed and costed and everything, perhaps back in 2019, perhaps 3 or even 4 years ago, to what extent has the state of the art moved on, and to what extent are you able to adapt within the project to that shifting sand around you and learn from it, or are you just sort of keep your eyes closed and hope that by the time you get to the end of your project, the world hasn't moved on too much?
I would assume this was a question to all of our presenters. So maybe Miguel, you want to start?
Yeah. Thanks for this question. It's not stupid at all as a question, in the sense that we do see that we live in a society of information, and the claims about battery technology, which are coming from all over the world, they are, in my opinion, very often overselling pieces of technology. I have read really everything and the opposite of everything, and I learned really to take with a grain of salt what is claimed about these batteries that can recharge in 30 seconds or can deliver solid state tomorrow and things like that. At the end of the story, we have really to be careful about interpreting these claims. There is one fundamental truth that the European industry is behind the schedule. If we compare state of the art in Europe, what we can do, what we can deliver, and what Asian industry, for instance, can deliver. And European industry, European battery manufacturing industry is not yet ready to deliver at the same quality, pace, and scale of non-European competitors. And we are catching up. And the fact that we are catching up is fundamental to our economy, to defend our economy, to defend automotive industry in most cases, since these are the first application for battery cells, but many others will come. So in our projects, in my projects in Tribelief, but I think that I can speak for all the projects, what we are building are the technology bricks for building up the European battery manufacturing industry. And we keep an eye on everything that is happening outside, but also we keep a focus, we try to deliver, and we try to catch up this delay that we do have as Europe in this strategic field.
Okay, maybe Jordan, you want?
Thank you. Thank you, Miguel. I support all your words, what you were saying. Also, I wanted to complement in the sense like, well, lithium-ion batteries have been going on from late of the 80s, right? So, and there has been many reports and many, but still, you know, lithium cobalt-oxide, you know, is still present in many cells, you know, coming at the commercial level. And obviously, that has moved to NMC, and graphite to hopefully moving to silicon at some point. So what I'm trying to say here is like, even though it has been many research, the technological gap is still there. So there is a lot of work to do. And I think, you know, that is the project that we are presenting here in a way that we are trying to close these gaps. And not just in terms of performance, also to keep the materials at the lower price and to be more sustainable, which is the three major topics of this call. So I think in that sense, so I think it is a great opportunity for all of us, you know, to complement and obviously I hope, you know, we can make nice apportations on these fields. Thank you.
Thank you, Jody. Michele, you want to add?
Yeah, no, I thanks them both because, yeah, the situation, of course, is that there is a huge gap between us and Asia, but I think that at this stage we can be happy about our results because, as you saw in all the projects, we are all having particular attention on the materials and the recycling and also to to push the projects to an industrial scales that can also reduce the cost of the manufacture. So I think that all of the projects that were explained today were really paying a lot of attention of all these critical aspects. So of course, as they told before, the gap is still there, but I think that they are all moving in the right direction. Yeah.
Thank you.
I don't know if
You
you
want
want
to
to
add?
add something.
Maybe to say that now we have more power of manufacturing. There is plenty of gigafactory that are planned now in Europe. To make better cell, we have to learn to make cell, whatever it is the technology. So I believe we will go much faster in the next year than what we saw the last 30 years.
Thank you. Maybe one question regarding recycling. It was addressed quite several times now, and I mean, what I'm learning is that technologies or particular material technologies quite well known, like steel, they need to consider now with higher recycling rates, higher impurities, and they really have rather difficulties to manage that. So maybe with the different technologies which you have presented here, could you comment on the long run, considering a fully circular economy, which means if you would have to recycle all the material, so we will end up with with a significant increase in impurities in the materials. How would your cells live with that? Maybe Kelly.
I'm not sure I'm the most right person to to answer to a recycling question. I can tell what I have seen around. Recycling industry is the other half of the coin of the manufacturing industry, and it is gaining momentum with a certain gap against the manufacturing industry, and that's pretty much clear. We do have in Tribelieve some activities concerning recycling. These are activities that will stay at lab level, and we target, if I'm not mistaken, 95% purity target. And I know that 99% is something that is possible, at least at lab level today. Whether this lab level will then become industry level, we will see. I think that there is a gap there to cover, but I do believe that in perspective, we can live with these impurities. As the technology develop, we will get more pure and pure material, and we can significantly decrease the reliance, the endemic reliance that Europe has on raw materials. So I have a lot of hope in that direction. I don't know if I'm just optimistic about that, but yeah, I think that's quite an important. That is okay. Does not work anymore. That's quite an important aspect.
Yeah, maybe you could also. I don't know. Guess what would be the effect on the energy density, or if could it be that like materials would kind of completely change the performance if there are just impurities simply because they are electrochemically, I don't know, a kind of a poison there. Maybe we have some technicians, or you hand over to me.
From LETAT, we will coordinate one on battery recycling. In the kickoff meeting will be on May. The name of the project is BATRO. And firstly, we do not plan to recycle everything. Basically, we focus on lithium, nickel, manganese, cobalt. Up to the dismantling, we select a specific type of battery because you have to adapt your safety process, dismantling process, etc. So I believe in the future you will have kind of factories for domestic battery or for the dismantling of domestic battery, other for car, on maybe the same plant of hydrometallurgical process from different black mass mixture, no? So to answer to your question, I do not know, but it is planned to be done in the framework of this project to retrieve the hydroxide lithium and the sulfate from cobalt and nickel at least. Manganese, we will do other things, and to make new battery with that and to see how it is impacting.
Yes, I think it does. Just following up with my colleagues, at Cobra, just for being specific, we have few tasks. It's not obviously the main target of the project of the recycling, but we're going to be looking just very briefly, at the possibilities, having the same targets of 95% recyclability of all the components as the 3 believe. But I also wanted to mention that I think with the recyclability also comes the second life of the batteries, right? So which is very important and something that we have to keep pushing on that. Eventually, everything has to be recycled, but we have to extend the life as much as possible. And I think this is something that we are already seeing, and we are already interested in really pushing, extending the life of the batteries. And this is something that industry and the new projects are clearly stating on their basics. Thank you.
Yeah. Maybe I can also add another thing that it's an economic problem in the sense that we don't maybe need to be completely independent in terms of supply of material. We just have to have diversified sources in order not to depend on a single stream. And this will economically change the market. So this might be sufficient. We don't need to recycle everything, but we might have different supply chains and different sources, and we can be much more independent just by that. So there is really an entwining with the economic problem and with the market and with the behavior of the market that needs to be considered there.
Thank you, Michele. There's another question in the back.
Yeah, good afternoon from my side, Noshinoman from EB. I have one question, one comment. Often we see in European projects some cost targets of 70 euros, 75 euros at pack level, even not on cell level. To which extent do you think it's realistic to apply such type of cost factors for the technology that you are considering, knowing that most of the manufacturing facilities in Europe are not ready to process such type of materials, and particularly not lithium, sulfur, and solid state at all. And we all know that the cost of solid state, the coming 5 years from now to 2030, is going to be factor 4 to 5, much more expensive than what we all know. So one point, because the processing cost. And maybe the comment is recycling. I think we can increase the recycling efficiency as we wish. It is just all about the energy and the cost matter. And it's going to come by time. Battery directive saves right now 55%. We are going to 65%. And the long term will go to 90 or maybe over 95%. It's a matter of time and matter of investment and upscalings. But nevertheless, we have still one problem, that all the recycling facilities in Europe are focused on nickel and cobalt and not on lithium iron phosphate. And that's really a very problematic issue. Thank you very much.
The cost. I think that this is a question for the Commission. So where does this cost target come from? This is a very good question. It's something that it's given by the economic viability of the battery. We do know that we have to go up to that cost level that for the LC-BAT 5 was 90 euro a kilowatt hour at a pack level. I think that for the cluster 5 destination 20102 last year was below 100 euros. So that's what we have to land in order to be economically effective. And how we land there is still a long path. So at the moment, I think that we do live on extrapolation on that. And extrapolation that also try to take into account the recovered value from the material in a full circular economy. Whether then it will be 70, 80, 90, 100, I really don't know. I think that no one knows as per today. Yeah, and I think that's the max that I can say now. Is there anything else?
Julie, you want to continue?
Yeah, it's working. No, I perfectly agree with him. Of course, the 75 euros is our target. Realistically speaking, the prevision we did specifically with the SiDrive project is around 150. So I think this is a more realistic one, but of course we have all to keep in mind that our final target, but it will be beyond the project, most probably by 2030. We will try to achieve the 75. So yeah.
Well, this is a very good question, Professor Noshin. Actually, I agree with my colleagues when we were preparing the cover. We saw that target of 90 euros per kilowatt hour pack level. Yes, now I think it works. So we were obviously struggling a little bit, how to really prove, that ambitious target. And eventually, obviously, we came all down to the cost and the using cheaper materials and more sustainable materials for all the components, right? And we make that projection. And it is difficult to prove that in a project that obviously goes or lasts for 4 years and is aiming for like 1 or 2 battery pack demonstrator, which eventually is not going to be cost effective. But the idea, I think the idea behind all this is like after 2-3 years, when it comes to the implementation, that we all expect to have this implementation at some sort of level. So we are having some tools, like really we can really help on that price target. Thank you.
Yeah, what I can say, Noshim is right. Manufacturing is not ready for lithium sulfur at the level of lithium ion, but sulfur is 20 euro kilo, much cheaper than an MC. And the manufacturability is pretty similar. No, once you have a dry room, so you have to add cost of dry room because not all lithium ion manufacturing today is done with dry room. On today, yes, we have only piloting installation, one in Italy, several in US, and GKM in Korea. But yes, we do not have the volume of what it is done today for lithium ion. But there is no reason for making it much cheaper than, much more expensive than what you have for an MC.
In 2008, together with my friends now at Mans, before it was Arcotronic at the time, we took 200 products in the world, okay? Nothing to do with batteries. And in this product, mainly the people at Mans, Stefano Saguanti and others, tried to understand what was the cost of the raw material and the final price. 200 different products, okay? And very surprisingly, the result was that the final price was in between 1.5 and 2. So whatever you develop, once you are mature in your development, the final price is 1 to 1.5 to 2, but very complex, including the cellular phone, okay? The final price is, if you add all raw materials inside, is 2 times. And then we came to the conclusion, tell me what you have inside the battery, I will tell you, as an old Fiat guy, I will tell you what the final price has to be. And the Chinese today, believe me, are indeed following the same approach. Okay? 200 products, not just one, okay?
Thank you for that comment. I guess it was more a comment than a question. This one better? Yeah. Okay, good. Yeah, looking again in the audience, we have a couple of minutes left for last questions. If there are no questions from the audience, questions from you, Johan? Not a question. Maybe I have a last question, kind of a summary for our presenters, having presented different technologies on anode, cathode, electrolyte system, sensors. If you would take out one of the technologies you're developing, what would be the most promising one? Would you bet, if you have to bet on, maybe, Michele?
Yes, I can start. Without saying the chemistry, because of course that's the core, that's the first thing that has to deliver. We have seen some exceptional results from our CMU, our cell management unit. Yeah. and we are already planning to scale this up to other type of application. So that's one of the technology that we'll definitely take from Tribelieve, and we will bring then in the next projects.
Well, this is a difficult question indeed. I don't know what to say. As a coordinator, I like all the topics that I'm involved on. So, well, I was less familiar with the silicon anode. So I think even though it has a lot of challenges, it also has a lot of potentials. And we still need to do a lot of full cell characterization to really understand, and to control, the ratio between the different electrodes and the negative to positive, and optimize electrolytes and so on. But I think that is a good material that in Cobra, as I said, we are working with recycled material, which I also wanted to point it out again, which obviously is the important loop and what we are discussing here, how to really recycle and materials that can be used for energy applications. Thank you.
Well, can you hear me? Yeah. I have a little conflict of interest because I'm representing all the consortium, but basically I'm working on the anode, so I have a conflict of interest. As Jordi told now, of course, silicon is a very promising material, but to be realistic, what is impressive and what we are really happy in our project is that we found the good combination within all the three main elements of the cell. So by identifying the most promising ionic liquid, we observed that this ionic liquid is perfectly matching both the characteristic of the anode and the cathode side. So in these months, we started in collaboration of our partner, especially the SiDrive, to analyze small prototypes of pouch cell. And we are very happy that the harmonization of the full cell is showing very good results in terms of stability. So if I have to be honest, I think that the good challenge was to find the good solution for having the harmonization of all the three elements that we are challenging since the beginning of the project. So yeah.
Well, for lithium sulfur, the battery cell by itself, I show some battery cell of more than 10 ampere hour at push-out level, with more than 400 watt-hour per kilo, on other with more than 1,000 cycle. So the challenge is to have both of them together in the same cell.
Yeah, with that, I guess we could come to the end of the Q&A session. If there is no immediate and very urgent question, from my side, I would like to thank the presenters, first of all, for the presentations. Thank you for a very interesting discussion, also to the audience for the good questions. And I don't know, Johan, if you want to make a final statement?
No, I just want to thank indeed Peter and all of the speakers. Thank you very much. Thank you to the audience for the excellent questions. Now we have a coffee break until 4 p.m. and here you see the next rooms that you can go to attend the next session. But first, coffee downstairs. Thanks to all.
And we are going to hear about the speakers, about what they have developed,